The slide presentation is looking at applied and industrial microbiology. Biotechnology is when you are using microorganisms, uh, and some of them may be having them carry out different metabolic processes in some way or form. You're going to use them so that you can have them produce a product or carry out some process that's a benefit to you. Fermentation is when you are using microorganisms. Um, in industrial microbiology, we use it a little bit differently. We're using those microorganisms in a very large mass culturing of them to produce large quantities of a particular product. Drinking water treatment, process usually will involve microorganisms to some point. You're going to vary the treatment depending on what your water source is. Usually in any type of a treatment facility, first there's going to be some sedimentation process where anything coming in, large objects, are allowed to settle out. Then you're going to use aeration, and then the final step will be a chlorination step. You're going to be monitoring for microorganisms because in the final step, as that water is released from the water treatment facility for drinking water, you want to make sure that there are no pathogens certainly in that water. And so usually you will have chlorination as that final step. Sewage water treatment facilities for large towns, cities, etc. So I'm not talking about private homes. If it's on a municipal system, there's usually 3 stages: a primary stage, secondary stage, and tertiary stage. Primary stage involves just removing any physical objects that come through the drainage systems. It's amazing what people will either flush down, pour down their drains, or if the storm sewers are connected to the sewage water treatment where it all flows through the same treatment, it's also amazing what people will put down there. So the first stage, before any type of treatment starts, usually there's a large screen. It's referred to as a grit screen, and that's catching all of these larger physical objects that then are removed before you start the treatment of the water. In the secondary stage, this is where you're going to be using microorganisms to help break down the organic material. And then the tertiary stage, that's going to remove any of the chemical pollutants, and prior to release from the plant, it will be disinfected with chlorine once again. Chlorine is a very effective thing for disinfecting water. From both drinking water and sewage treatment plants, you need to be monitoring that water, the effluent, the water that's being released. Usually what you're going to be looking for is making sure there's no fecal contamination in there. So you're going to take a sample, you filter it, and you do place that filter on a selective medium. And the identification process, you are looking for coliforms, specifically, usually fecal coliforms. For drinking water, though, you'll be looking for total coliforms. Sewage water, it's the fecal coliforms, specifically E. coli. If E. coli is present, that is indicative of recent fecal contamination. So from the sewage plant, you're probably going to have some E. coli there. So you want to make sure that you have cleaned that out before it's released back into the environment. This is showing the fecal coliform. As I said, it's a selective medium. The blue colonies are what ideally you don't want to see. That would be E. coli. And so you would count the number and calculate how many bacteria. Usually you do it per 100 mils. And EPA does regulate how much or how little can be in there. Obviously you want it as ideally nothing. There are some limits you cannot surpass. For the water monitoring, you're going to typically be looking at total coliforms. How many are allowed? It depends on what that water is going to be used for as it's released from the facility. If it's going to be used for human consumption, obviously the standards are much stricter than if it's just going to be used for non-human consumption, like say watering the golf course. And this is what the total coliforms would look like. You would end up having to count all of those. And once again, EPA sets what the number can be. You would not want to be drinking this water. Microorganisms, a lot of people, especially in a microbiology course, start to have kind of a fear of them because we spend so much time telling you about the medical microbiology and how you get the feeling they're all out to get you. They're all these pathogens, and all they want to do is make you sick and kill you. And I try to balance that by saying, no, that's not all true. Only about 5% of the known microorganisms are human pathogens. So most of them are good guys. Most of them, frankly, don't really even care about us. And so one huge area that I try to do is show some of these other examples of how microorganisms are involved, whether it's bioremediation, whether it's nutrient cycling, and certainly a huge area is food microbiology. So we use a lot of microorganisms to produce food. How do we use them? Often by fermentation methods. Bread, cheese, wine, beer, yogurt, pickles, all of those you would not have without microorganisms. Oftentimes you have to maintain a starter culture, and all that's referring to is the microorganism, the culture that's going to be added to the food. And this just, I've selected several random different pictures showing you of different foods that you would not have if it were not for the microorganisms, or you would use it like the grapes for producing foods. For a bread, specific species of yeast will give different flavors. The yeast is going to ferment the sugar when you add it in. Any of you who bake bread at home know this, that you're preparing the dough, you have the sugar in there. The yeast, you add the yeast, it's going to ferment that sugar, it releases carbon dioxide. That's what's causing the bread to rise. Baker's yeast is Saccharomyces cerevisiae. Sourdough bread uses a different yeast. It gives it, once again, this different, unique flavor to it. Lactobacillus San Francisco is the one that's used for production of sourdough bread. For beer, to produce beer, what it is anaerobic fermentation of different fruit and grains by yeast. It's producing, once again, ethyl alcohol. So you need to have water, you need to have malt, the barley, the hops, and the yeast. When alcohol concentration reaches between 3 and 6%, it's automatically going to stop. It will not continue beyond that point. Wine is the fermentation of any fruit. Usually it's grapes, but you can use any fruit. You need to crush the fruit. It needs to be fermented, then stored. After storage, it needs to be filtered, and then it's aged. Differences between red wine and white wine. White wine is using either white skin grapes, or it can use red grapes. Excuse me. However, the skin has to be removed prior to crushing. White wine tends to be fermented longer than red wines. Red wine's going to use red or purple skin grapes. And I included this in just to show you some of the basic steps of making a red wine. As you can see, there are multiple steps in here. You've got to harvest the grapes. They're going to be crushed for red wine with the skin on. You would add sulfite. That's going to kill any undesirable yeast and bacteria that may have been on the grapes. You then add the specific yeast inoculum that you want to carry out the fermentation process, which will then start occurring. After the fermentation, you're going to go through a process where it's pressed. You're going to separate out any of the solids from the liquid portion so that excuse me, the wine's going to be clarified. You let it settle. You then filter it. It's then aged, and finally it is bottled. There are several different types of alcoholic drinks that are made using this similar fermentation process. It just depends on what the starting material is as to what alcohol you get, depends on which type of yeast you're using. So just a generalization, if you're using sugar cane and you're fermenting that, distilling, you end up with rum. From potatoes, you get vodka. From various grains, you can get whiskey. And from grape, peach, or apricot wine, you get brandy. So none of those alcoholic drinks would be available if it were not for the microorganisms. A lot of foods are fermented. Cabbage, when it's fermented, that's how you get sauerkraut. You get pickles from cucumbers. Cottage cheese, yogurt, and cheese all come from milk. So none of those would be available without the effect of microorganisms. For cheese, how do you get the different types of cheese? Part of it is adjusting the amount of water, fat, acid, salt content in the overall composition. Some cheese is ripened, where it has a special curing process. It just depends on the specific type of cheese that you're making, and also, once again, which microorganism are you using. Remember, pasteurization is a form, especially dealing with, say, milk, where what you are trying to do is kill the pathogen, but it doesn't sterilize. If you were to completely sterilize the milk, it tends to alter the flavor of it. So oftentimes we go with a high temperature pasteurization. You increase the temperature to 72 degrees Celsius for about 15 seconds. Therefore, it does not affect the flavor. Industrial microbiology is where you're using microorganisms to produce various chemicals, products that you are wanting, that you can then purify, sell it for whatever purposes. Things such as antibiotics, food additives, solvents, enzymes. There's a whole list of things that can be used for.